So let's then take a look and see what happens if we have resistors in parallel. So if we have things in parallel, it can literally mean that they're in parallel, but really what it means is that we are at a decision point in our resistor world. So let's say we have a 5 ohm resistor, a 12 ohm resistor, and a 20 ohm resistor. All right, now picture our little electron dude, and he's like, woohoo! Where is he going to go? He's obviously going to go here where the 5 ohm resistor is. And his little friends are all going to go where the 5 ohm resistor is. But then eventually what's going to happen is you're just going to get a ton of little dudes in the 5 ohm resistor line. And then you're going to have like independent thinker. You can tell he's independent because he has a goatee. Independent thinker is going to be like, I'm not going to stand in line for the 5. I'll just go to the 12 because it might be a longer line, but at least I'm first in line. So then you got little dude, and he's like there, and little dude is there, and little dude is there. Now, further along the line, you get like awesome sauce chick who's like chick electron, that's like, hey, I don't want to stand in line with all those bozos. I'm going to come over here and like be in my own little spot. Okay, so there are going to be more people in the first line, but it doesn't take as long to get through. There's going to be a medium number of people in the second line, but it takes a little bit longer to get through. And there's going to be also almost no one in the last line, but it takes longer. But essentially what happens is the amount of time it takes, and this is a bad example, parallel, but it'll be fine. This amount of time that it takes for everyone to get through is exactly mathematically the same. So the way we describe this is the pressure across each one of these, across each one of the lines is the same. Now remember though, that we don't really talk about pressure. That's not exactly the right word. So we're using the word voltage. So when you have things in parallel, the voltage across all the lines ends up being the same because everything's trying to even out. So if you have 100 amps going in, you still have 100 amps going out, but you don't have the same amount of current going through each one. So we say that the current is not the same. Okay, so the voltage across each one of them is the same, but the current going through each one is not the same when things are in parallel. Now, the equation for resistors in parallel, the equivalent resistance, is a weird equation. So 1 over the equivalent resistance is 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance, all over to however many resistances you have. So in our case, the equivalent resistance is 1 over 5 plus 1 over 12 plus 1 over 20. Actually, the way I write it, and I don't see anyone else doing it this way, but I kind of got stuck in my head, is the equivalent resistance is 1 over 1/5 plus 1/12 plus 1/20. And that's just simplifying and, multiplying both sides by, or dividing, both sides by 1 or whatever. Taking the inverse of both sides. How about that? So I like doing it that way because it works into my calculator a little bit better. So if I've got 1 over, make sure you've got all your parentheses in there, 1 over 5 plus 1 over 12 plus 1 over 20. So it actually gives you an equivalent resistance of 3. On your 89, that's going to look like basically the same thing, where you've got 1 over 1/5 plus 1/12 plus 1/20, and I get 3. So the equivalent resistance of all of these is 3, which is kind of weird. I'm going to have to zoom out so you can see this a little bit better. So what you look at when you see resistors in parallel is actually the 3 here is smaller than the smallest. Smaller than the smallest. You're smaller than the smallest R in the original circuit. So 3 is actually going to be smaller than 5, 12, and 20. Because whenever you have, think about it, if you have a super, super slow cashier and another kind of slow cashier, but then a fast cashier, between the 3 of them, they can still get more people through the line than the one super fast cashier. So when they work together, there's the least amount of resistance. Okay, does that kind of make sense? All right. So if we have, say, I don't know, the let's say we have the 100 amps going in here. Now we still have the high voltage and the low voltage. So 3 times 100 is 300 volts going through, and there's still 100 amps coming out the outside. Okay, I'm going to erase all my little angry electron dudes as best I can. So I still have 100 amps going through, but I do know now that the pressure across all of them has to be the same, or the voltage across all of them has to be the same. Okay, so I'm going to move some stuff out of the way so I can keep coloring. You go over there for a while. Okay, so each one of these has to have, what did I say it was? 300 volts across each one. So high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. So 300 volts, 300 volts, and 300 volts. Now again, because I know that V is equal to IR for the first one, 300 volts is equal to the first current times the resistance, which is 5. So I1 has to be 60 amps. So I know that there's 60 going in here, which means, of course, that there has to be 60 coming out. Now, I also know that V equals IR. So the voltage across the second one is 300 volts. The current, I don't know, but the resistance is 12. So I2 has to be 25 amps. So 25 coming in, 25 going out. All right, then I have V equals IR. There's 300 volts. The current, I don't know what it is, but then the resistance is 3. So 300 divided, it's got to be 15. Yeah, 15 amps. So there has to be 15 amps of current going to the last one. And for those of you who are super duper on top of things, you know how I know I'm right? Do you know how I know I'm right? Do you know how I know I'm right? Because I have 60 going in, and another 25 going in, and another 15 going in, and hallelujah if that's not exactly 100 amps. Same thing here. I have 100 amps coming in, 60, 25 plus 15, that all equals 100 as well. So whatever's going in has to come out. All we've really done here is looked at how the resistances in the different branches affect the ratios of how those particular electrons get distributed. So again, the biggest thing that you want to kind of pay attention to from this kind of perspective of resistors in parallel is that, I've moved over here, that the voltage across all the lines is the same, but the current is not the same. Okay, so that's kind of a key takeaway. The voltage across things in parallel is the same. And also the idea that 1 over the equivalent resistance is equal to the sum of all the other 1/overs. Okay. Now, if you're not sure if you're in parallel or series, the way that you know you're in parallel is if you have to start making a decision. Now, how shall I say this? When you take circuits for real, this is just kind of an intro to circuits, so this can kind of percolate for the next, however long till you really take circuits. Things can be in neither parallel nor in series, but in general, if you're approaching something and you're not really sure what you're doing, if they're in parallel or not, they don't actually have to be drawn in parallel. So for example, I could draw this coming in here, and this coming in here, and this coming in here, and this could go wee doo wee doo wee doo wee doo woo, and they could all like connect over here. And basically, I still have 3 things in parallel. I just have some idiot who has way too much free time on his hands and puts wires together in a dumb way. So I'm still going from A to B in just the most obnoxious way possible, but these are still in parallel. This could be just a giant dollop of solder, could put all those together. So I have 2 nodes, node and node, and everything in there shares those 2 nodes. So basically, I could just come in and cut this wire shorter and cut this wire shorter, and I would have the same picture that I had before. So again, you can have something that looks like this. They could also be kind of curvy wires, but remember that when we're drawing pretty circuits like this, that's not how they're necessarily going to be in real life. We're just drawing them to make them pretty. But you can get some more practice at that.